In this video for section 13.9, another application of optimization, we're going to use a second partials test to answer the question. A retail outlet sells two types of riding lawnmowers, the prices of which are P1, P sub 1, and P sub 2. Find those prices so as to maximize the total revenue. Now this revenue equation has already been generated, and we get R equals 515 P sub 1 plus 805 P sub 2 plus 1.5 P sub 1 P sub 2 minus 1.5 P sub 1 squared minus P sub 2 squared. All right, so we want to find the prices that will yield the maximum or maximize that total revenue. Now we do have P1s and P2s here. You may, if you like, rewrite this equation. So you get R equals 515, replace any P1 with X, and replace any P2 with Y to get this equation with X's and Y's. And notice that this is an equation of revenue in terms of two variables, so it's a function of two variables, so you can use the second partials test to determine the relative extrema. So let's take the partial derivative of this function with respect to x. Treat x as a variable and y as a constant, and that partial derivative is going to be 515. The derivative of 805y is going to be 0 because we're treating y as a constant. The derivative of 1.5xy is going to be 1.5 times y. We're treating x as a variable. And then the partial derivative here would be 2 times negative 1.5 or 3x, and the derivative y squared would be 0. So we want to find out that first partial derivative, where does that equal 0? And then the partial derivative with respect to y. Treat y as a variable and x as a constant, and you get the partial derivative is 805 plus 1.5x minus 2y equals 0. Here we have a system of equations. It's a system of linear equations. I'm sorry, I made a mistake. I just noticed that this term here should be x, not y. So notice, again, we have a system of linear equations. We can use a substitution method, the elimination method, or we can use the matrix method. In order to use the matrix method, we do want to write the system of equations in that form. Negative 3x plus 1.5y is equal to negative 515. And then when you rearrange the terms here, you get 1.5x minus 2y is equal to negative 805. Okay, so you're going to plug in just the coefficients here, 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 and these numbers into the matrix, and then enter the calculator command to reduce row echelon form of that matrix with the values as shown. Okay, so quickly with the calculator, I've already gone ahead and entered those values into the matrix. Again, you go to the matrix window and go to the edit tab and edit the first matrix. Now to get out of this screen, you do want to press second quit, and then I go back to the matrix menu, choose the math tab, and scroll down until you see the command for RREF. Oops, went too fast there. Second matrix, go back to the math menu and enter the RREF command, and then go back to the matrix menu and enter the name of the matrix you want to reduce, and here we get our matrix. So the solution to this system of equations is that x is going to be 596.667. These are prices, so this is going to, they would make the price 596.67, and the price for the second lawnmower would be $850. Okay, So by solving that system of equations, we get x equals 596.67. That would be the price of that first lawnmower, and then y would equal $850. So those are the two prices that would maximize the total revenue. So P1, the first price, we could say is 596.67, and P2 would be $850. Now, if you're asked what would the total revenue be, you can plug those values into your original equations for P1 and P2, and you would get, I think, approximately about 53 million in revenue based on those prices.